So here's our third example on inclined planes. Particle of mass 2 kilograms rests on a smooth plane, and we're used to this now, but not all questions will be in a smooth plane when we come to the exam. So smooth plane, so there's no friction here, inclined at 30 degrees to the horizontal. And this time we've got a pulley question, so it's connected to it by a light, inextensible string. And don't forget from our pulley work previously, this means that the whole system, the tension in the string is constant and the acceleration is going to be constant throughout the whole process of this question. Okay, so that passes over a smooth pulley at the top of the plane to a particle of mass 3 kilograms, which is hanging freely. So we're asked to find the acceleration and the tension in the string. So again, our first thing to do is to draw a diagram. So let's have a look at this. We've got an inclined plane, inclined at 30 degrees to the horizontal. So there's our 30 degrees. And we've got this particle of mass 2 kilograms resting on this plane. So that's weight 2g down. And this is connected, it says, to a pulley. So we've got a pulley here. This is connected to our pulley by a light, inextensible string. And then here, our second particle, which has got weight 3 kilograms. And that's just hanging freely there. Okay. So this is what's happening. Let's put some other forces on. Again, that's all we're told in this question. But let's make sure we put all our forces on our diagram before we start answering this question. So at this point, we've got a reaction from this 2 kilogram mass, perpendicular to the plane, perpendicular to the surface here. So that's our reaction here. This one's just hanging freely, so there's no reactions or anything here because there's no surface in contact here. I've drawn it a little bit poorly because it looks like it's sitting against this. Should have drawn it with a bit of a gap, I suppose. But this is just hanging freely here. Okay. What else is happening then? Well, we've got tension in the string, and this tension in the string is going to be acting there against this weight and here against that weight. So there's our tension. And it's the same tension because it's the same string passing over this. It's light and inextensible. So there we go. Okay. The other force that we've got then is this 2G. And just like in our last two examples, we need to look at our parallel and perpendicular components to this plane here, because this is the motion, direction of motion that this one's going to be in. So this line of action here, we need to look at parallel and perpendicular of our 2G force. So let's put that on. We've got one component acting that way, another component acting that way, where the resultant is going to be this. This is 30 degrees, so this is going to be 60, and I could use 60, but I'm going to get used to doing that idea of using this one as 30, sort of matching this angle, so that if it's an unknown, if it's alpha or theta or something like that, I can work with the same angle there. So this is going to be 2G cos 30, and this one's going to be 2G sine 30. So I've replaced now my 2G weight, and I could scribble this out, I suppose, with these two components. Okay. We've got different things happening here now. So we've got a pulley question. So I'm going to consider my two weights, my two particles separately, just as we've done with a pulley question when it was all in the vertical plane. We consider A and B. So I'm going to consider my 2 kilograms and my 3 kilograms. And just before I do that, I want us to get into the habit of checking the direction of motion. So I just want us to look, sorry, let me just change colour there. I just want us to look at the direction of motion here. Okay. So is it going to end up going that way, or is it going to end up going this way? Okay. And you might look at this and think, well, that's fairly obvious because this is 3 kilograms and this is only 2. But I want us to look at this component because it's only this component that's trying to pull this one down the plane, whereas this is 3G pulling this one down the plane, across the plane that way. So that one, 3G, acting downwards, but this one, the component of the force that's trying to pull this one back, is just our 2G sine theta. So let's just check. Sorry, sine 30. Let's just type that in. So 2 times 9.8 times sine 30 So that's 9.8 there. And then our 3G is obviously 3 times 9.8. So this is definitely winning, and our force here, our 3G, is going to be forcing the motion to go in that direction. I want to put that on our diagram so that when I come to do my resultant force equations, I'm definitely going in the right directions here for positives and negatives. And just to be clear, let's just say if this was 4 kilograms, we might think if this was 4 kilograms that this would definitely pull back this way, but let's just have a look at that. So 4G sine 30. And actually then, even if this was 4 kilograms, let's say, 19.6 is less than the 29.4. So even if this was 4 kilograms, this system would still tend to go in the same direction as this one does. Whereas as this one's getting bigger, obviously you can see, as this one's getting bigger, this force starts to kind of win, and the actual resultant motion will be down this way. So just get into that habit, please, of checking that first of all. Even when you think it's completely obvious, just make sure you check it before you know which direction you're going in. Okay, now let's have a look at our 2 different masses. So let's have a look, first of all, let's have a look at the mass, the 3 kilogram mass. So the 3 kilogram mass, if I'm taking down as positive, because that's my direction of motion, so I've got 3G, my tension is trying to pull me back, and that's going to be equal to MA, so resultant force equals MA. It's not in equilibrium now because this thing is accelerating in this direction. If we were told it was in equilibrium, then it would be a different question, wouldn't it, where the resultant force is 0. And this mass is 3, so that's 3A. I've got 2 unknowns, so I'm going to end up with simultaneous equations. There's equation 1. Let's have a look at our 2 kilogram mass. Again, resultant force is going to be equal to MA here, because we have definitely got some motion in that direction. I'm going to look up the plane as positive. So I'm going in that direction. And in this question, I'm not bothered about the reaction. It doesn't ask me about the reaction. But if I was asked about the reaction, or in later questions when we do questions on friction and the reaction is involved, obviously then I could look perpendicular and say the resultant force is 0. But let's look up the plane, up as positive. So tension, pulling it forwards. 2G sine 30, that component of the weight tending to hold it back. That's going to be equal to 2A this time because it's this mass. We've got a second equation there. I'm going to ask you to have a look at solving these then. So we could add these 2 equations together, or you get T as the subject here and substitute it in here, or get A as the subject. Doesn't really matter. I'd probably get T as the subject here, substitute it in, find out A, and then sub back in. So what I want you to do is to solve those simultaneous equations. I'm going to go dot, dot, dot. You should end up with then to 3 significant figures. A is equal to 3.92 meters per second squared, and the tension, so acceleration 3.92, tension T 17.6 newtons, and they're both to 3SF. Please don't just write those down though, please do this dot, 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 have a look at doing the algebra and check that you get those 2 answers when you round them to 3SF. I'm going to set you some work to do then on this topic, resolving forces when it's on an inclined plane, and then next few lessons we'll look at tension and we'll start to, we'll look at friction, and we'll start to look at some more complicated questions.